Hello. Welcome to another operational amplifier example. And I guess this circuit can be quite a surprise. I'm not sure whether I'll name it for you or not. But let us begin. This is a very recent question, and I noticed that in the recent op-am question, the questions are actually a little bit anomalous or a little bit different. They like to ask you to do the dreaded state and explain a bit more often. Okay, but don't worry. First, we're going to start off with definition. So 8A is asking you about the properties of the ideal op-amp and pretty basic stuff. Okay, so it says here that an ideal op-amp is connected to a load resistor. Sure. Op-amp is assumed to have infinite bandwidth and zero output resistance. So they already tell you some properties already. Yeah. If they ask you to list down other properties, you cannot use these two, okay? Write out the other stuff. There's an entire list. Okay, but in this question, they're not asking you to list down the rest. They're asking you to state what is meant by infinite bandwidth. So a student with infinite bandwidth, right? The brain can study many things. Can study chemistry, can study physics, can study maths, can study further maths, can study bio, can study econs, can study all the things. Infinite bandwidth, all subject knowledge gain is the same. Ideal student, ideal processor, ideal op-amp. So this means for infinite bandwidth, we are saying that there is a constant gain. So it's not like, I don't like physics, so I put it one side. And then I don't gain in physics as much as I gain in chemistry because I really, really love chemicals. Me too, bro. Me too. Okay, anyway, constant gain for all ranges of frequency of the input voltage. So sometimes, if you remember from your comparator circuit, your input voltage can be AC. So don't care whether the AC got high frequency, low frequency, the gain is the same. All right? Unless you change the resistor purposely, then you are changing the gain. Okay, anyway, state the effect, if any, on the output voltages, so you want to know whether V out will be affected by increasing the load resistance. Okay, maybe in this case, it's better to draw the circuit. So you got the op-amp, the good old phi connection that I don't really care about here and here. What we care about is V out. Okay, V out is here. A bit small, but this V out is connected to a load resistor and then nothing else already, so I'm going to assume that it is grounded. So it is said here that it has zero output resistance, meaning here, this output here got no resistance. R is zero. Or impedance is a better term. Okay, so the output impedance or the output resistance is zero. Now when that happens, right, this means all the V out is expressed across the load. So here to here will be V out. Because this is zero, and this point here is V out. So V out minus zero is V out. So if you increase this load resistance, I'm just going to label this load resistance. I need a face massage. Load resistance. This is R. So if you increase this R, will you change your V out? Well, my friend, you say, no. Miss, why not? Well, if you increase the resistance, you don't change the potential, you decrease the current, remember, from your DC circuit. Okay, so at this branch, right, when you think about it, the current will just flow slower when the resistance increase. The potential won't change one because the work done per unit charge is the same, but now you have to work harder, so your work is slower. Okay, so from here, the answer is it remains unchanged. Remains unchanged because the op-amp, or an ideal op-amp, I guess, doesn't affect the V out across the resistor. Okay, so you increase the load resistance, the only thing will happen is that the current will decrease. So the current that is flowing through here, let's say there's a current, I don't know whether VR is positive or negative, let's say it's positive lah. So this value of I will become smaller. Okay, this value of I will become smaller. We'll later, I guess, do an example about this. Okay, but so you know, changing this R will not change the V out. V out must only change, and V out can only change because the V in change. So for ideal op-amp, right, V out should only change if and only if V in changes for the same circuit. You never change the connection. So the only reason why V out will be different inside the op-amp is when V in change. Okay? When I say change the resistor, I mean change the feedback resistor lah. Alright, you change this resistor, no problem. You change the resistor that's directly connected inside here, then no problem. Okay? So think about that. We're going to move on to B. Wow, look at this monster. A student designed a circuit in order to indicate changes in temperature of the thermistor. How apt, because I have a boiling laptop now. Anyway, change in temperature of thermistor T. So this is thermistor T. Yeah, this one, so many resistor. 4 resistor, 1 thermistor. Such a pain. Okay, never mind. Part 1. Explain why point P is known as the virtual earth. So if this is virtual earth, wow, very sus liao. Virtual earth means inverting op-amp. Yay! Okay, another clue would be V plus is grounded. Okay, so what to explain? Very standard. Don't know you hear how many times already, but I quickly write lah. So this is how you can memorize facts like this. Whenever you see it in your past year, don't skip. Just spend 2-3 minutes writing. Okay, so you can say that the gain of the ideal op-amp is very large. I guess you could also put infinite lah. Okay. Second point here, you could say any changes or any differences between, I'm changing up the sentence, inverting input and non-inverting input, okay, saturates the output. And we don't want saturation. No. Okay. So we prefer that. So to prevent saturation, and furthermore, since V plus is grounded, so V plus is 0 volt. Scroll up a bit. V plus is equal to V minus. V minus is also 0 volt, known as virtual earth. Okay, so that are the main ideas. You don't want the op-amp to saturate, right? You think about the previous example where I talk about the voltmeter. So your output is 5. 5 is not yet saturate, 9 only saturate. If you wu tuan tuan, you put small reading saturate, you put big reading saturate, you put everything also saturate. What is the use of this op-amp? Besides turn on traffic light lah. It's like student, you know, you teach one thing, saturate. You teach 10 things, also saturate. No difference already, your entire brain is saturate now. Okay? So you want to prevent that from happening, meaning you have to ground yourself. Isn't there some life philosophy here? If you don't want your brain to saturate, you must ground yourself to your values, to your belief, to your priorities. What is important to you? Okay? So here, the gain is very large. So we want to prevent saturation. V plus is grounded, so V plus must be equal to V minus. So V minus is also grounded, but not really. So that's why we call this the virtual earth. Alright, 3-4 marks explanation in the pocket. Nice and easy. I'm going to move on to the next one. Hiya! Calculate the potential at point Q. Very curious. See what I did there? You see what I did there? Never mind. Very curious to find the curious potential at point Q here. I'm just going to call this VQ. All right. So if you stare at this, okay, you go like, Miss, I understand. I know, I remember this one. This is a potential divider. Good job. So if you remember this is a potential divider, check out the connection of the battery. This is a positive terminal. It is connected. I'm aware you can't see my mouse. I should make this thicker. Like how I like my coffee. Thick, black, and dark. Okay, anyway, this is connected like this. So this is positive 1.5 volt. Alright. Miss, this one is what, my friend? Our entire downline, downline, if I sound like an MLM. Entire bottom line here is grounded. Everybody is 0. My favorite number, bruh. So this is 0. Very nice. Okay. So now we can use ratio. All right. They're asking you to find the potential of Q. VQ is actually the potential from here to here. Okay, I'm just gonna do. Here to here is VQ. Okay, so we can use ratio. All right. So I will use the ratio of potential VQ over the whole thing lah, 1.5, which is what Miss Ellie taught you. Okay. I guess I should crop the circuit over. I be back, and this is the potential divider. So you want to find VQ, right? Okay, so I'm going to use ratio. I can ratio the whole thing if you want to. Okay, this entire ratio here to here is 1.5. I'll draw the arrow. 1.5 volt. Okay, so what do we do? Ratio 1.5 over the total resistance 110 plus 40, and this will be equal to, let's just take VQ over 40. Now if you're used to the way I usually write this, I will rearrange, and VQ will be 1.5 over 110 plus 40 times 40. Sorry, my version looks like this. Preference is just a matter of preference. 40 over 110 plus 40 times 1.5. Whichever lah, you're happy and you understand can down, because this will give you 0. Let's press calculator together. 40 over 150. My ancestors is scolding me for using calculator. Girl, where's your abacus? Sorry, mom. Casio is my best friend. Alright, so this is 0.40V. Okay, so 0.40. Alright, so I just want to explain some stuff to you, okay, in case you are not aware of this. The potential across 40 ohm is 0.40. Meaning the potential across this one, if you ever need to find it, for whatever reason, will be the remainder, which is 1.1 volt. Now use your big brain, which I'm sure you have. By the way, please write 2SF. 2SF. Okay, don't lose that mark again. Never ever again. Okay, anyway, you look at this 0.40, you look at this 1.10. When you add these two together, you get 1.5. But when you ratio them, it is 11 to 4. 11 to 4. Okay? Second thing here is, it's like climbing up steps. You start from 0, you climb 0.4, you become 0.4. Alright, so here is 0 volt. Here is 0.4 volt, because here to here is 0.4. The difference is 0.4. Okay? And you climb up here again. This is 1.1 volt. So 1.1, 0.4 plus 1.1 is 1.5 volt. 0.4 plus 1.1 is 1.5. Ratio of 1.1 to 0.4 is the same as the ratio of 11 to 40. And 1.1 plus 0.4 is 1.5. So this is ratio. However, you learned ratio last time in kindergarten, primary school. Make sure you understand that, because if not, then you're always thrown off guard, or you memorize the steps without really understanding what you're writing. Time to level up. All right. So let's move on to part 3. At temperature 13 degrees Celsius, oh my. 13 degrees Celsius temperature. Okay, stop freaking out, OneNote. You can do this. Alright, so 13 degrees Celsius, the thermistor is 230 kilo ohm. Show that the potential difference measured by the voltmeter is 0.88. Chinese New Year number, very nice. Alright, so we want the voltmeter reading to be 0.88 volt. So let's go and peek a bit at the circuit. Alright, so if you want this to be 0.88, meaning the potential here, because this side is 0, right? And I'm assuming if they say 0.88, they mean positive 0.88, right? Miss, I don't know. Never mind, I don't know. It's okay. It's okay. They didn't say, so it doesn't matter. You have to trust yourself. What they didn't give, you don't need. But this is, let's say this is positive, okay? For the sake of discussion, then this is the negative connection. Alright? Because we have talked about the voltmeter in the previous example, remember? Alright, when we connect the voltmeter. So if this is a positive reading, then I can assume this V out here is positive, just to make my life easy. I'm generally not a very positive person. When it comes to circuit, I am. Alright, so you can see that this feedback loop looks a bit sus. Why? Miss, normally the feedback loop only got one resistor. Why now they put 2 resistor? Hiya, one not enough meh? Why must have 2? Okay, so if that's what you're thinking, well, it is a little bit anomalous, but these 2 resistors are in series, one after the other. So if you want to find the total resistance, you can just combine them into one big happy family. And total resistance here in the feedback loop will be, I guess, T, or I think maybe I put RT. RT plus 100 kilo ohm. So you can assume that they are 2 in 1 married together. Okay, so on one end here, you have positive 0.88 V. Point P here is virtual earth, 0 V. The other side here, VQ is 0.4 volt. Just now calculate already, 0.40 volt. Miss, we can draw. What can we draw, my friend? We can draw the potential divider. I'm so proud of you. If you're thinking about that, you're right. You're right, guys. There's another potential divider here. Connecting point Q to P to V out. I'm going to label myself a V out. This is V out. Connected to here. Okay, so I'm going to straighten my beautiful resistors. You want to start from where? 0.4? Positive 0.88? You want to modify something? What is happening? Okay, you come down first. Let's say I start drawing from 0.88. Started from the top, and now we're still here. Okay, anyway, 0.88 volt. If you're unsure about the polarity, leave it first. So here is a combination of these 2 resistors. I'm going to just call these 2 100 k ohm plus RT. I mean, I don't know what RT is. Did they say? Oh, they got more? 230. Right. So this will be 100 kilo ohm plus 230 kilo ohm. Very nice. All right, moving on. Eventually, you will meet point P. Okay, VP is 0 volt because this is virtual earth. So in case you don't know, I have simplified the blue loop into this resistor. Okay, they are in series. I can add them together. And if you want to, here is V out. Okay, this VP here is 0 volt. Miss, I got suspicion. Yes, what is your suspicion? My suspicion, or Miss, since this is 150 kilo ohm, is that this one down here, since this Q, VQ is 0.4 volt, we cannot have positive on both sides of 0. Yes, so smart of you. So if both sides of 0 cannot be positive, what's going to happen, Archer? How, Archer? How, Archer? Okay, this means we need to bring in the dreaded negative sign. Okay, so if this is a negative sign, like legit, if this is a negative sign, then you can, what you need to do is you just need to flip the connection. Okay, so the positive terminal will be connected to the ground. So this one is positive, connected this way. Okay, and the negative terminal, as mentioned just now, connected here. So this is not positive, it's negative. Okay, but don't worry about it. They just want the magnitude. So how do you show the potential? The voltmeter reading is 0.88. So in this question, right, they're actually asking you to show the 0.88. Information overloaded. Okay, we need to show this. That means we gotta pretend we don't know. Shy, don't know. Okay lah, don't know, then you can delete it or you can cover it. You don't want to see it. Okay. I delete. Okay, so we don't know. We want to find V out. Okay, so voltmeter reading, that's the first thing I will write. Only 2 marks, I wouldn't have bothered to write so much lah. But voltmeter reading, in this case, when connected properly, is V out. Okay, so V out is across this one. You can use the potential divider again, but use it slowly. All right, so the potential difference across here to here, here to here, down here is 0, right? So this is just V out minus 0 if you want to. Okay, so I will use ratio. V out minus 0 over the resistance 100 plus 230 kilo ohm. Miss need to convert. I will decide later. Next. Okay, the next portion is here, here to here. Okay, if you don't really care about the negative sign, you can omit it. You can just say that the potential difference here is 0.4. You know why not? Because they just say potential difference. They didn't say potential. So when it comes to difference, what we are looking for generally is magnitude. Magnitude only. Okay, so you can, I guess, just for propriety's sake, I will use 0. This one will be 0, the higher potential, minus, no wait, I'll take the lower minus the higher, higher minus the lower. I think 0.4 minus 0 lah, to make my life easy. Okay. In fact, you don't minus 0 also okay. 0 in the middle, very convenient one. Here, the blue one is V out, the green one will be 0.4. Okay, so we're trying to show V out. Okay, don't forget to ratio the resistor. This is 150 kilo ohm. Bless you, kind sir. Kilo ohm can cancel. So if kilo ohm can cancel, we can rearrange our calculation. Here you will have V out is equal to cross multiply. This will be 330 over 150 times 0.4. So this number will give you 0.88. Let's pray. 330. Joking. Very nice. 2.2. So this is 0.88. Miss, where is the inverting? You are using the analysis that you learn while deriving the inverting input equation to apply on a brand new circuit. Normally, they will tell you what VQ is, but now they being fresh, they connect this entire circuit here as a potential divider. I'm going to draw this part here. This whole circuit, or this whole thing is the potential. Okay, let me scroll up a bit so you can see. This is the potential divider to set the potential VQ. I set the value of this 0.4 by adjusting the 110 and 40. By setting the 0.4, I will set the output. Setting this 0.4 will set the output. Now, normally, they'll just tell you input is 0.4. And then you're like, but why? You know, why is the input 0.4? So this is how they can set the 0.4 by just connecting to a different potentiometer. All right. So in this question, this is one of the methods. You could use ratio, or you could find the current. Because this op-amp or current cannot flow inside one. Why? Because of large input resistance or input impedance. AKA, you just need to think that the op-amp is a no man's land. Current cannot go in. So the only way for your current to flow is like this. Ding, ding, ding. Okay, so you can use V equal to IR 2 times. All right, so I will very quickly show you this method. Okay, so I'm going to write down there because I'm running out of space a bit. So this is part 3. Alternative. So I'm going to focus on the 150k ohm resistor. Okay, potential difference here is 0.4 volt. Potential difference here is 0 volt. This is point P, this is point Q. Whoops, my head is blocking, sorry. All right, 150 kilo ohm. Potential difference here is Q, potential difference here is P. We can use V is equal to IR. Our good old V equal to IR, 0.4 is equal to I times 150 kilo ohm. So I guess you can press your calculator here to find your find your current. -3. I mean, it is not a very nice number, so I'm going to keep this in fraction form because it's an intermediate answer. So this one would be 8/3. Right? Am I wrong? Hang on. 0.4 150k. Oh no, 8/3 micro times 10 to the power of -6 ampere. All right, and very soon you'll be able to see why I insist on using this value. Wait, is this correct? Sorry, I'm not used to slow methods, so sometimes the brain will hang. 0 point, because the values all very sus. Only 3. 2.667. That's 8/3. 10 to the power -6. Do we round? I'm not going to round, okay? Because the answer will change too much. So I'm going to write times 10 to the power 3 like this. I'm going to leave it this way. Okay? This is the current. Now, if you want, you can press, but your value may run. Okay? So next, once we have the current, we know that this current is flowing inside the resistor. So this is the green part. But what about the blue part or the feedback part? So the feedback part, one side is point P. Connect to your, this one is your 100 kilo ohm resistor. Connect to your RT. Connect to your V out. Okay. The current in here, I, is the same as the current in here. 100 ohm, RT, P, and V out. Let's look at this one. 100 kilo ohm, RT, point P is here, V out is here. Okay, and the current is the same current. This is I, which is your 0.4/150k. All right, so I'm going to continue this train of thought. Whoops, bypassed. Okay, so I'll use V equal to IR again. But in this case, I'm looking for V. V will be V out minus VP. Okay, the current we have already, 0.4 over 150 times 10 to the power of 3. And the value of R is 100 times 10 to the power of 3. So the times 10 to the power of 3 or kilo can cancel out lah. And VP happen to be 0. Okay, so this will be 0.4 times 100 over 150. That hopefully will give me, did I divide something wrongly? Let me see. Oh, I forgot about RT. Like I said, not used to doing. So if you're thinking about me, what about your RT? Sorry. Not used to doing the long way. Not wrong, just long. So you can see if I'm not familiar with the method, I will make mistakes along the way, but I can correct because they gave me the final answer at 0.88. All right, so learn to fact check yourself this way. Okay, so what happened here? What I forgotten was RT has a resistance, so I should include RT. This one has no problem. This is not 100. This is 100 plus 230 kilo ohm. Okay, so it is 100 plus 230 times 10 to the power of 3. So 10 to the power of 3 and 10 to the power of 3 can cancel out. And what we will have here is 330 over 150 times 0.4. Okay, correct now. This is 80888, 0.88. Proven. Okay, so you could use this alternative method. You use V equal to IR on the green part, V equal to IR on this part to find the current. Because current cannot enter op-amp, so all the current will flow through this blue part. Okay, then you can use V equal to IR for this blue color part, this part from here to here, to find the value of your V out, because this side is 0 ma. Okay, or you could just use a simple straightforward ratio like this. That way you don't have to go and find I, because it came from the same equation if you remember the derivation. All right, so that's it for this part. Let's go to part C. All right, part C. Let us zoom in and read it. The resistance of thermistor T is decreased as temperature rises. All right, no problem. RT will drop. So RT decrease. State and explain, or rather explain the effect of this change in temperature on the potential difference measured with the voltmeter. So basically they're asking you, how will V out change? Okay, let's trace back our calculation. Okay, if you look at this method, right, you can actually see that the V out has a certain gain. Okay, so if we treat 0.4 as your V in, because that is the other end of the input, right? If you treat 0.4 as your V in, let me modify this again a bit. I can say that V out over V in is actually 330 over 150. How you know? You ratio the feedback resistance, which is this entire branch, to 150. Right here. Gain is RF over R in. I guess can put a negative here lah. RF is RT plus 100 and R in is 150. This is your gain. Okay, so I'm going to write here just for us to look at it. Gain in this regard, gain is equal to RT plus 100, the magnitude of the gain. If you want to, we'll put a negative in front to make you feel better. Okay, so gain is equal to negative RT plus 100 over 150. So with this equation, it's easy to explain. Okay, so when RT decreases, resistance of thermistor decreases. What happens to the gain? The gain of the op-amp drawn in the circuit decreases. So if the gain decreases and gain is equal to V out over V in, V out decreases, and what happens to your voltmeter reading? Okay, so because of this, PD measured by voltmeter also decreases. So where are the 2 marks? First mark is when you mention that the gain of the op-amp decrease. Second mark, you say V out then decrease. Gain decrease, so the multiple decrease. And the multiple decrease, that means the potential difference measured by the voltmeter decrease. So here is the same idea. We, instead of putting your RT at the thermistor at the potential divider input, we can put it at the feedback loop, because that will actually adjust our gain, and based on our gain we'll have a different potential meter reading. We can feed that reading into a device to display to us what the temperature is. Okay, so hopefully this question is helpful. You can see that sometimes you can always use the same skills over and over again. Of course, you can save some time, and I can save some saliva if I just tell you to find the gain, which is negative RF over R in. And there's a time and place to use those equations, provided you still know this in your arsenal. Okay, if not, then sometimes if the circuit look a bit complicated and you don't know how, and the technique of straightening out the circuit and using ratio to find potential divider, it's pretty important, guys, once this one show. Okay, so we use the potential divider method twice. One is a straightforward one to find the 0.4. One is a slightly more convoluted one to find the 0.88. You can use a more steady method, which is to find the current first, and then use the current to find the potential difference. Just be a little bit more careful. And lastly, you notice that when the temperature change, the resistance will change. When the resistance change, the output will change. So if let's say the output decreases, I can actually know that, oh, the temperature is actually increasing, and I can display this on a thermometer. All right. So if you are interested in trying more questions that look like this, where we use a sensor in a negative feedback circuit, specifically the inverting input, okay, you can try out these 2 questions. All right. The year is given to you. So we will put LDR and the thermistor at different parts of the circuit, and you should be able to interpret the changes and also know, oh, if the temperature increase, if the temperature decrease, what happens? Because sometimes the older question, they don't ask you something like this, which means they could re-ask a similar circuit and ask you to explain what happens, say, for light intensity changes or the thermistor's temperature changes. Okay, so go try out a few questions. These 2 are my suggested questions. There's also an entire list in the description box or in your task or your homework, your assignment. If you find this video helpful, you know what to do. Share with your friends. Okay, op-amp can be quite confusing. So let's learn this and game this together, because it's all about looking at circuits quite differently than how you used to do so. So with that, I wish you good luck in your A2. Please go try some pass here, and I will see you in the next example video. Bye-bye.